Mr. Tarrou, in this lesson we are going to be taking a look at Newton's method to approximate the zero of a function. Zero, root, solution, x-intercept, all those names mean the same thing. Where's the graph crossing the x-axis? In this lesson we're going to do three examples. The first one is going to be algebraic, the second one is going to involve some trigonometry, and the third example is going to show how sometimes the Newton's method is going to fail us in estimating a zero. You can skip ahead to those examples. I don't know, I'm pausing. You can skip ahead to those examples. I'll put this timestamps in the description of this lesson. And remember that we have already learned many ways of solving equations. We've solved linear functions, just getting the x by itself. We had lots of ways of solving quadratics. We've factored, we completed the square, we used the quadratic formula. And then in pre-calculus, when we started solving higher order polynomials, we had to use the rational zero theorem to list off a bunch of possible rational zeros, and then use synthetic division and Descartes' rule together to try and help minimize the amount of trial and error and break down that polynomial until it got down to a second degree. And then we, started using that quadratic formula or factoring to finish out the problem. So we already understand that a lot of equations are hard to solve. Once you set them equal to zero. But maybe with this idea of Newton's method, we can take some equations that are, differentiable and maybe even pretty easy to differentiate, but yet hard to solve for zero and estimate those zeros another way, the Newton's method. We're going to let tangent lines estimate, or we're going to use tangent lines to estimate the zeros of a function. So here we can see that there is a sign change between f of a and f of b, and f of x is continuous on the closed interval from a to b. Well, yeah, we could see it if I wasn't standing in front of my graph. So on our green fancy picture-in-picture, we have a smooth, continuous curve here, f of x. It needs to be smooth and continuous. Just continuity is enough for the intermediate value theorem, which I'm going to talk about in a second. But we're also going to be talking about and using derivatives. And we need to have a smooth function because you can't find a derivative at a sharp bend or a break, other, interesting points on a graph like that. So we have a smooth and continuous graph here, a function. And f of a is positive and f of b is negative. So there is indeed a sign change. So you can go from positive to negative, or of course vice versa. And if you see that sign change, and the function is continuous on a closed interval, thus the intermediate, or when that's the case, the intermediate value theorem is going to guarantee at least one zero on the open interval from a to b. At least one, could be more. And if solving for f of x is very difficult, we can estimate the zero using tangent lines. Well, a tangent line, what do you need to write the equation of a line? You need a point and a slope, and the slope is where the derivative comes in, of course. We know that by now. So let's get this out of the way and look at the three steps that we are going to need to work through in our three examples. We're going to, for Newton's method, let f of c equal 0. So that's just simply saying that we're going to let c be the x value for which the function is equal to 0, or it's crossing the x-axis where the y value is 0. Where f is differentiable on an open interval containing c. So we have the open interval of a from a to b, and that open interval is surrounding the area where the function crosses the x-axis. We're going to make an initial estimate of x sub 1 close to c. Close to c. Them long distance relationships are difficult and a lot of times they don't work. You don't want to pick an initial, I call this z because, well, I've got an initial estimate of an x-intercept or a 0 here, but if you just say for temporarily let z equal x sub 1, or this is my initial estimate of r0 that we're trying to estimate. Well, if it's too far away from c, the slope of the function could throw you a tangent line that goes just nowhere close to this 0 that you're trying to estimate. So you don't want to be real far away because you just simply, might have the Newton's process may fail. So we want an initial estimate that's close to c. Then we're going to determine a new approximation based on an initial estimate, that x sub 1 that I'm talking about here in the first step, or previous iteration. So basically what you're going to do is you're going to just, come up with equations of tangent lines over and over and over again, and in between find out where they cross the x-axis. And from each of those, well, I'm babbling. Let's just look at the picture. If I let this x sub 1 be my initial guess of the 0 of the function, it's kind of like telling a calculator, graphing calculator, you know, hey, what's your first guess? Where do you think the x-intercept is when you're trying to find your root or 0 in the calculator? From that x sub 1 value, x sub 1, we have here x sub 1, y sub 1, or f of x sub 1, we come up with a tangent line, which is just a linear function. And it's really easy to find an x-intercept of a linear function. You just isolate x. You don't even have to factor or, you know, even set the equation equal to 0. You just get x by itself after, you know, letting y equal 0. And then from that new estimation of this 0, you make another tangent line. And you can see that you're going to progressively move closer and closer and closer to the 0 of that function. And actually, within just a few steps, I'm showing here basically one guess and then 2 tangent lines. You might have to do 3. You'll get close to that 0 quite quickly. So let's see here. How do you write the equation of a line? I just said it, sort of. Or that's what we're going to do. We have y minus y sub 1 equals m times x minus x sub 1, point slope form of a line. We have our initial guess of the 0 and the y value that comes from it. Now in the next line here, I'm not, this formula is in your book. You know, this is the formula for coming up with the iterations or the list of possible or estimations of the 0 that you're looking for that are getting closer and closer and closer, hopefully. And it's just the formula in your book, but I want to show you where it comes from in case, you know, later on down the line you forget the formula. So we just have point slope form of a line. We're letting y equal 0 because obviously that's how, you know, when you cross an x-axis, the y value is 0. So the y is disappearing. And we're trying to estimate a new x. So we're trying to sort of, our initial x and our initial y, the slope of the function based off of that initial estimation, of course. And so this first line would be like you finding the equation of this blue tangent line. Y is equal to 0. We're going to divide both sides by the derivative or f prime of x sub 1. And then we're going to take that x sub 1. Now it's in this derivation, it's a variable, but that x sub 1 is going to be a number. That's going to be your initial guess of the the x-intercept. So we're going to add both sides by x sub 1 and x sub n. I'm bringing these subscripts in because we're going to, again, use a sequence or a list of just new tangent lines based off the previous tangent lines. And so we have x sub n is equal to x sub n minus 1 minus f of x sub n minus 1 over f prime of x sub n minus 1. So what the heck does all that mean? It just simply means we're going to find a new approximation of the 0 based on the previous one. These subscripts are just basically where you are in a list of values. So take a guess, come up with a tangent line, find out where it crosses the x-axis. From that point, come up with a new point. So we're going to take that x sub 2, plug it into the function, and get a new y value, so a point along the function, a new derivative or a new slope based off of x sub 2 as opposed to x sub 1, and come up with a new tangent line. Now this is blue, that's purple. We make that new tangent line. We find the x-intercept of that purple or that next tangent line, and if you aren't close enough yet, you just repeat the process until you get within a certain margin of error that meets the requirements of your problem. And that is the process of working through the Newton's method. Now, if the absolute value of x sub n minus x sub n minus 1, your new estimated 0 minus your previous estimated 0, if the absolute value of that difference is within the desired margin of error, let x sub n be your estimated value of c. And if not, just repeat the process. Now, when you tell your graphing calculator to estimate the 0 or find the root of a function, you have no option of telling the calculator how accurate you want that estimated 0 to be. If you're doing the Newton's method by hand, well, you have some control over that. So let's get to our first example right now. For our first example, we're going to approximate the 0 of this function. F of x is equal to 7 times the square root of x plus 1 minus 4x. using Newton's method and continue until two successive approximations or iterations differ by less than 0.01. Now, the book that you're learning from may say that it's a good idea or okay to use a graphing calculator to get a picture of this graph and then use the graph itself that you get from the calculator to come up with that initial estimate for C, that initial estimate for the root or the zero or the x-intercept. But I know that there's a lot of universities that do not allow their students to use a graphing calculator at all in their class. So I'm going to give you the sketches of these graphs, but hopefully at universities when they give you these types of problems, they're not going to be that terribly difficult to come up with that, that interval where the function changes sign. So let's see here. Yes, I typed this into my graphing calculator and I got this sketch, but let's pick some x values that we could easily end up with a value that we could easily square root. Like, how about if we let x equal 0? Well, f of 0 is going to be 0 plus 1 is going to be 1, and so we have the square root of 1, which is 1, or 7 times, well, I'll leave the square root in there. 7 times the square root of 1 minus 4 times 0, well, that's going to come out to be a positive 7, and I don't even really care that the answer is 7. I'm just looking for going along and testing some x values until I find that sign change, so I can use that or understand that the intermediate value theorem is going to tell me, oh, there is an interval where we have a sign change, and thus somewhere on that open interval you have at least one zero or one solution or one x-intercept. And I don't want to try and take the square root of 2 or 3 or 5. Taking the square root of 4 is good. The square root of 4 is 2. So I could let x equal 3. F of 3 is going to be equal to 7 times the square root. Well, 3 plus 1 is 4. So we're taking a look at the square root of 4 minus 4 times 3. And the square root of 4 is 2. 2 times 7 is 14, and 14 minus 12 is equal to 2. Which again, I don't really care that I know it's 2, just that we have another positive answer, but it is getting smaller. So let's try taking the square root of 9 is easy, so let's let x equal 8. And if we find f of 8, we're going to have 7 times the square root of 8 plus 1, which is 9, so the square root of 9, minus 4 times 8. Well, now we have 7 times 3 is 21, and 21 minus 32 is going to be, what, negative 11? And it's going to be negative. So we have a sign change between the x value of 3 and the x value of 8. Now, at f of 3, we're still positive, but we're not that far above the x-axis. And at f of 8, we're all the way down to negative 11, unless I've made an arithmetic error somewhere. And, we're quite negative. So I'm going to let my initial value, my initial guesstimate of what this x-intercept is, I'm going to let that be 4, because we're closer to 0 at 3 than we are at 8. So we're going to let x sub 1 equal 4. Okay, that's my initial guess. Now, what we're going to do is we're going to find a tangent line. We're going to come down here. Now, this isn't drawn to scale or anything, but I hope it's not complete garbage. But we're going to come down from 4, make a tangent line, and let that tangent line help us find an estimation of that 0 and see how close we are. And again, we're trying to do find these iterations until we get a difference of less than 0.04. So let's see here. If that's x sub 1, then x sub 2, my next iteration, my next estimation of the 0 based on my previous guesstimate, is going to be equal to my initial guess of 4 minus, okay, now here, let's see here. We need to find the function's value. Well, I could just write it down. X sub n is equal to x sub n minus 1 minus f of x sub n minus 1 over f prime of x sub n minus 1. So we need to find the function's value at 4. Okay, so we're looking at minus 7 times the square root of 4 plus 1 minus 4 times 4 over the f prime of 4, or my initial, my previous estimate of the 0. Okay, well, f prime, well, yeah, we need to find the derivative. So let me come off to the side here. Should have maybe done this first. F prime of x. Okay, well, now this is 7 times x plus 1 to the 1/2 power. So if that x plus 1 is to the 1/2 power, we bring that 1/2 power down out front, and 7 times 1 over 2 is 7 over 2 times x plus 1. Now I'm taking the derivative using the power rule, so we're going to decrease that power by 1, so that 1/2 now becomes negative 1/2. And we don't have just a simple base of x, it's x plus 1, so just make sure you check that chain rule. So power down, decrease the power by 1, and now we're going to multiply by the derivative of the inside function, but the derivative of x plus 1 is just simply 1, so we don't need to really show that, unless you want to write a times 1 there. Minus the derivative of, with respect to x, of 4x is just simply 4. So writing that in with a radical notation and getting rid of this negative power, the derivative is going to be 7 over 2 times the square root of x plus 1 minus 4, except of course we're not writing the derivative down there. We're using the derivative to tell me slope. We're finding the slope at 4, so we're taking the square root of x plus the square root, excuse me, of 4 plus 1. Get my story straight, and then right off the top of my head, all of this, get this, just type this all into your calculator if you can. Be careful of your parentheses, or hopefully you have a newer graphing calculator that allows you to use math type. And if you get all this typed in correctly, your x sub 2 value, the estimated value of x sub 2 is going to be approximately equal to 3.8573. Now, the difference between 4 and 3.8573 is certainly greater than 0.01. So with Newton's method, now that you understand this formula, remember I gave you the derivation on that previous screen, just keep going through this process until you get an estimation that's close enough. So x sub 3 is going to be equal to, based on the previous iteration or the previous estimate of our 0, 3.8573 minus, now we have to find a new tangent line. So we're now going to use the 3.8573 just like we use the 4 up here. We're going to plug it into our function and then plug that x value into our derivative and start off with that x sub n minus 1. So we have the 3.8573 minus 7 times the square root of 3.8573 plus 1 minus 4 times 3.8573 over, now its derivative, 7 over 2 times the square root of 3.8573 plus 1 minus 4. And that is going to be approximately equal to x sub 3. Right off the top of my head, voila! Right off the top of my head, that comes out to be 3.856594. Just running that out. And look at, now we could see that this graph drops very drastically, and it's not vertical between or at this 0 here, but it's pretty darn steep. So within just, I guess technically that's our first guess, and then 2 more iterations, we are becoming very, very close to that, actual c value, that actual 0 or root. And on our x sub 3 value, our third iteration, The approximated 0 is 3.8566. And that's the end of our first example. Now this is the process. I'm going to come up with another example, our second example. It is going to involve some trig functions. Probably just go ahead and display the question and reveal the solution one step at a time, because it's the exact same process with our formula for Newton's method right here. All you have to do is make sure the function is continuous and differentiable on that open interval, and use that formula to work through the iterations of estimating the real 0, the root. Bang! Alrighty then, I forgot that I gave a nice little twist to this second example. We're not initially appearing, it doesn't appear to look like we're finding x-intercepts. So let me set this up and then we'll reveal the solution one step at a time using Newton's method. Apply Newton's method to approximate the x values of the indicated points, those two red points right there, of the intersection of the two graphs. Those two graphs being f of x is equal to 2x squared minus 1 and g of x is equal to the cosine of x. Didn't I just spend a couple of screens or scenes with you talking about how Newton's method helped us to approximate zeros or x-intercepts? This is finding the solution or a value of x where two graphs are intersecting. Well, yeah, I mean, we've been solving systems of equations since what, Algebra 1? And all we have to do is come up with an equation that represents this idea of setting these two equations equal to each other and then setting that equal to 0. So there's some value of c such that, I don't hope this green shows up off of the yellow, but there's some value of c such that, with having a function that's, we're talking about sign changes on a closed interval and functions which are differentiable on the open interval and all that good stuff. But basically, we're looking for a value of c such that the y value from each of these equations is the same. So solving systems of equations using the substitution method. So if the cosine of x has given us some value and the cosine of, or 2 times x squared minus 1 is given us the same value at some particular value of c, well then those y values are going to be the same, and we get that 2x squared minus 1 is equal to the cosine of x. And having this idea of its some x, these two functions giving me the same y, setting up this equation, then I can set it equal to 0 and say that we've got, that I really kind of meant to turn this around, but well, we can say that we're going to subtract both sides by 2x squared and then add 1 to both sides and get 0 is equal to the cosine of x minus 2x squared plus 1. And that is our function. If you like, you can call that function h of k and, work through the Newton's method to approximate that 0 or approximate, this parabola and this cosine function intersecting, setting those equal to each other, getting us this new equation that we're setting equal to 0. We have to start off with that initial x sub 1 value, our initial guess of where these two functions are meeting, or where that function is equal to, that h of x function is equal to 0. And these are certainly graphs that I would expect my students to be able to sketch without the aid of a calculator. And, basic parabola, maybe you might need to test, do a couple of points to come up with this sketch. But certainly we should understand what the standard, graph of cosine of x looks like, and come up with the idea that these graphs are going to intersect somewhere within these values of negative pi over 2 and positive pi over 2. Well, pi over 2 is 3.14 divided by 2, which is approximately, what, 1.57? So I think a good reasonable guess as to where these functions are crossing is going to be an x value of 1. So we're going to let x sub 1 equal 1, and now let's work through a couple of iterations of that Newton's method. And it'd be a good idea to pause the video and try it on your own and see if you get the same answers that I do. So there you have it. In just one guesstimate of a value, x of value of 1, and just going through 3 more iterations of the Newton's method, we have an estimated value, a solution where these functions cross, of 0.90037. We went from 1, coming up or using that tangent line and using the next intercept of a tangent line, we get 0.905. From that next iteration, coming up with a, basically using the next step, the next equation of the tangent line based off of that estimated 0, we get a next step of 0.90038, and then going one more iteration and trying to find x sub 4 based on that initial guess of x sub 1 is equal to 1. We work through, and our value, our estimated 0, only changed by 0.00001, so quite accurate there by just going through a few iterations of Newton's method. Now, that means that when you plug, and if your calculator is in radian mode, 0.990 or 0.90037 into this function f of x and g of x, you're going to get, basically, they won't be exactly the same because this is just an estimation, but a very accurate one. You should be getting very, very close to the same y value from each of these functions. So at that value of c, these functions are effectively intersecting. Now, what about this other red intersection point? Well, let's not forget even functions. Even functions, and yeah, if we're studying calculus, we probably don't need this review, but just to make sure. Your even functions are those functions that are symmetric to the y-axis, and you can see that by that f of negative x is equal to f of x. Or in other words, you plug in those opposite values and you get the same value out. Well, the cosine function, you can see here, if we fold this graph on the y-axis, is going to line up on itself. The cosine function is even. And with this polynomial, having this very basic polynomial, the only variable of which has an even power, that parabola is going to prove to be an even function as well. So if this intersection point has an x-coordinate of 0.90037 approximately, then this left intersection point is going to have the same value except for simply negative. So our x values are basically plus or minus 0.90037. Now, sometimes the Newton's method for approximating zeros leaves you in a bit of a bad spot. So let's take a look at our last example. Bang! So as you saw, we were going to, or asked to, apply the Newton's method to estimate the 0 of that function using this initial guess of x sub 1 is equal to 2 pi over 3. Okay, again, Newton's method, of course checking the fact that the function is differentiable in the open interval and, you have a sign change in that closed interval, all the conditions have been met. It's just x sub n is equal to x sub n minus 1 minus f of x sub n minus 1 over f prime of x sub n minus 1. Basically just a new estimated 0 is going to be based off of the previous one, whether you came up with that iteration or it was your initial guess. And we're given our initial guess. So if this is our f of x function, then f prime of x, the derivative of sine is cosine, the derivative of cosine is negative sine, that's why we have the sign change. And where did the 2 go in the numerator? Well, our inside function is 1/2 x, and the derivative of 1/2 x is simply 1/2, and 1/2 times 2 is equal to 1, and this is our derivative. This is our f prime of x. So, with our initial guesstimate that's given to us of 2 pi over 3, x sub 2 is equal to x sub 1 minus the sine of x sub 1 minus 2 square root of 3 over 3 cosine of x sub 1, just plugging that initial sort of guess of the 0 into the original function, and then the denominator we're plugging that 2 pi over 3 into, of course, the derivative. Okay, the sine of 2 pi over 3, using our unit circle, is square root of 3 over 2. The cosine of pi over 3, after those 2's cancel out, is equal to 1/2. The cosine of 2 pi over 3 is negative 1/2, and the sine of pi over 3 is the square root of 3 over 2. Great. Well, when you start to work that out, work out the Newton's method, since our derivative is in here in the denominator, our derivative, f prime of 2 pi over 3, ends up coming out to be, well, negative 1/2 plus 1/2 is equal to 0, and you can't divide by 0. So this is just one example where Newton's method is going to fail to give us the next iteration, and thus we have to stop the process of trying to estimate the 0. Now, you can just work on, go pull up that original graph or sketch the original graph, the graph of this original function, and maybe, just pick an initial value of x sub 1 that is closer to the 0, if indeed there even is one. And for that particular problem, whatever it is you're working on, probably as if it's in your textbook, and just work through it then. This particular initial guess gave us a derivative which was equal to 0, and thus stopped the process because it became undefined. And you'll find other examples in your textbook and homework where that caused the Newton's method to fail. This is just one particular example. And this is the end of my last example. I'm Mr. True. Go do your homework.